problem. Here NaOH on dissociation, we will get Na plus and OH minus. Here there is no H plus. So concentration of NaOH is 0.01 molar. This is also 0.1. This is also 0.01 molar. Here we can calculate from this expression, we can find the value of pOH. pOH is negative logarithm of concentration of OH minus I. So we will get negative logarithm of 10 raised to minus 3. 10 raised to minus 3, that is equal to 3. Here we got only pOH. Then after that, this equation pKw is equal to pH plus pOH. We already learned this equation. pKw is 40. pH we don't know. pOH is 3. So pH will be equal to 14 minus 3. Oh, we will get 11. So it is a base. So we can calculate pH of acid and base. Next is calculating the equilibrium constants of weak acids and weak base. Before that, we have to study about the degree of ionization or extent of ionization. It is represented by the letter alpha. So we know that molecules on dissociation, they will produce positive and negative ions. This is undissociated molecule and dissociated ion. Their ratio is called degree of ionization. So degree of ionization is defined as the ratio of dissociated molecules to the total number of molecules. That is, number of molecules or number of ions after dissociation or after ionization divided by initial number of molecules, that is total number of molecules. So from the extent of ionization, from the degree of ionization or from alpha, we can say whether it is a weak base or strong base. So we are going to study about the dissociation constant or equilibrium constant for weak acids and weak base. Actually they are called not equilibrium constant, they are called ionization or dissociation constant. First for weak acids, and that is represented by Ka, dissociation constant for weak acid. So consider a weak acid. So, acetic acid. All organic acids like acetic acid, formic acid are considered as weak acids. On their own dissociation, they will undergo only partial dissociation and form CH3COO minus ion. It is called acetate. That is a common name. Acetic acid on dissociation gives acetate and H plus ion. So after some time they will reach us in an equilibrium. So we can write the equilibrium constant. Equilibrium constant. Equilibrium constant K is equal to, what is the equation? CH3COO minus into concentration of H plus, that is products, divided by concentration of reactants. It is represented by the letter K. Here, initially let C is the concentration of acetic acid. Then alpha is the degree of dissociation. Initially the concentration of C, they rub this for writing. Okay, concentration is C. Then here the concentration is 0 initially. Then let alpha is the degree of dissociation. That means C into alpha, that is a percentage, will undergo dissociation. So here the C alpha, C alpha. What will be remain here? Initial concentration is C. Then C minus alpha molecules converted into ions. So remaining is C minus C alpha. Here C alpha, C alpha. So substitute these values in that equation for equilibrium constant. Can I have this? So Ka is equal to CH3 concentration of acetate ion into concentration of H plus ion divided by acetic acid, concentration of acetic acid. So on substituting these values, we will get C alpha concentration, C alpha, that is concentration of acetate, concentration of H plus, divided by C minus C alpha. On simplify C alpha into C alpha, C square alpha square divided by, take C outside, 1 minus alpha. So 1 C will cut. So we will get the equation C alpha square divided by 1 minus alpha. So Ka is equal to C alpha square by 1 minus alpha. This is the equation for calculating equilibrium constant for a weak acid, that is called acidity constant, where C is the concentration of the solution, alpha is the degree of ionization or degree of dissociation. Then for doing problems we can simplify this. Then if the degree of dissociation is very less for some cases, the value of alpha is very less, so that we can negligible, that is 1 minus a very small number is almost equal to 1. Then alpha is very less, then 1 minus alpha is almost equal to 1. Then the equation will become Ka is equal to C alpha square, or alpha is equal to root of Ka by C. So using this equation we can find the degree of dissociation alpha for weak acids. There Ka is the acidity constant and C is the concentration, that may be given in molarity or molality. So these are the expression for calculating acidity constant and degree of dissociation. The same way we can derive an equation for a weak base also. Here only one difference, instead of Ka we'll get a Kb. Okay, we'll go to that also. Basicity constant or dissociation constant for weak base, represented by Kb. So consider a weak base. Consider a weak base, that is ammonium hydroxide. Ammonium hydroxide on dissociation is NH4 plus and OH minus. It is a weak base. There is not complete dissociation, only partial dissociation. There is an equilibrium between undissociated molecule and dissociated ions. Then initially let's see is the concentration. Initially the concentration of NH4 plus and OH minus is 0. Then let alpha is the degree of dissociation. So C alpha molecules will convert C alpha, C alpha, C alpha. So remaining C minus C alpha. And here C alpha, C alpha. Then Kb is equal to products by reactant, that is concentration of NH4 plus into concentration of OH minus divided by concentration of NH4 OH. Substituting the values, we will get C alpha into C alpha divided by C minus C alpha. Simplifying, we will get Kb is equal to C alpha square divided by 1 minus alpha. Using that equation, we can find the value of Kb. Kb is called a basicity constant or dissociation constant for a weak base. Then from this equation, by approximation, we can calculate what that is alpha. We can calculate alpha to, that is Kb by C. Where Kb is the basicity constant and C is the concentration. So we can calculate Kb and alpha. So these are all about dissociation constant for weak acid and weak base. So next, so based on the dissociation, there are two types of acids, that is strong acids like electrolyte, strong acids, weak acids. I will give you some example for strong acids so that it will be easy for you. Then all mineral acids like HCl, HNO3, H2SO4, then perchloric acid, all these are example for strong acids. Then weak acids, organic acids, acetic acid, benzoic acid, then the carbonic acid that is present in soda. All these are examples for weak acid. Then strong bases. Strong bases and weak bases. Strong base, that is metals with low ionization enthalpy like sodium, potassium, calcium, all their hydroxides will be strong bases. Then weak bases, very good example for a weak base is ammonium hydroxide, then silver hydroxides. These are the examples for a weak bases. Then sodium bicarbonate. All these are examples for weak base. So metals of low ionization enthalpy, their hydroxide will always be strong base, others will be weak base. So just understand the difference between strong and weak for doing some calculation based on that. Sorry. Next we will study about another effect that is called common ion effect. It's a very important one. So common ion effect we can explain using Le-Chatelier principle, that is we already learned in the another class. So common ion effect means, consider a weak acid or base, anything we can take, should be weak, that's only one condition. So here we took the dissociation of acetic acid. We know that acetic acid is a weak acid, it will not undergo complete dissociation. Let its dissociation is 70%. Initial dissociation or at equilibrium, or it will undergo only 70% dissociation. It's an example, not an approximate value. Then, so this is now exist in an equilibrium. So we already learned that the system at equilibrium, if we try to change any one of their properties like pressure, volume, temperature, concentration, etc., the system will try to nullify that change. Then here there are CH3CO minus or H plus ion or acetic acid. This system at equilibrium, if we are adding one of these ions, either CH3O minus or H plus ions, what will happen? Suppose we are adding CH3COO minus. Then the concentration of product increases. System will to try to decrease the products by shifting to what's left. That is, backward reaction takes place. So what happened to the extent of dissociation? Is it decreases or increases? Yes, here it will decreases. That is called the common ion effect. That is a decrease of or suppression of dissociation of a weak electrolyte by the addition of a salt with a common ion. It is a suppression or decrease of dissociation of a weak electrolyte by the addition of a salt with a common ion. So here we are not adding this ion. Instead of that, we are adding sodium acetate. Sodium acetate is a salt and it is a strong salt. So when we are adding sodium acetate to this,